Hey, good morning, guys. Assalamu alaikum. Welcome back to grade 12, Physical Science by Inspired Teens. In today's lesson, we are going to be continuing with work, energy, and power. Okay, before we do continue though, can you guys please confirm that I can be heard, my screen can be seen? Okay, cool, perfect. Thank you so much. Okay, so I'm pretty sure today, all right, I said last week, we're gonna continue with we're just gonna finish up work energy power and finish up with some questions, right? So let's go ahead and let's do this question. A 3 kg object is moving up a slope, okay, with a constant speed of 5 meters per second. Frictional force does 50 joules of work. Find the power delivered by the applied force. Okay, this one is interesting. So, firstly, what they're actually asking for power, let's just discuss the formulas, the possible formulas that we can use for power. The possible formulas we can use for power are as follows. Okay, we have okay, we have P is equal to W over T, okay, and we have P is equal to force times velocity. Okay, we have two options for this one. So in order to calculate power, okay, we can take the work done, by the way, of course, like think of it this way, right? They want this is really important. The sentence is really important. They want the power delivered by the applied force. Okay. So since they want the power delivered by the applied force, anything that we'll need to substitute into this formula is going to be about the applied force. Anything that we're going to substitute into this formula is going to be about the applied force. So for example, if we're going to use the second formula, it would be the power of the applied would be equal to the force of the applied times its velocity. Okay, velocity of the object. So just keep that in mind. Okay, if they wanted, just say we're using the first formula, power of the applied would be equal to the work done by the applied divided by the time of that work being done on that object. Okay, so just keep that in mind. So if they had to ask for the power done by anything else, you'd know then what to substitute into the formula. Okay, so here, right, we're dealing with a question. Okay, we're actually supposed to have a drawing. Okay, this object, which is 3 kg, is moving up the slope with a constant speed of 5 meters per second to the -1. Okay, and what else should be given? Okay, two other things are given. The first thing that's given is that this here, the angle here is 30 degrees, and the delta x that it travels, okay, is equal to 10 meters. Okay, that's also given. Okay, so remember I said, whenever we're dealing with work energy power, there's two formulas that I want you to keep in mind. Okay, the first of which that we should think of, or rather, depending on whether there's the existence of frictional force applied and tension, or if there's no frictional force applied or tension. Okay, so in this case, we have frictional force. So what's the first formula that we should always try? WNC. Okay, so let's write out WNC. Let's write out our formula and let's see if we can substitute values. Okay, remember WNC, delta U, this is going to work with height and mass, both of which we're working with. and delta K, that works with velocity, okay? And we have, of course, mass and velocity, and we have a velocity, right? Now, WNC, we're going to open it up, okay? So now we have to consider all the non-conservative forces acting on this object as it moves up the slope. So remember, we said the only conservative force that we work with is gravity. That's the only conservative force, okay? So everything else would be a non-conservative force. So firstly, there's definitely frictional force, because it tells us that frictional force does work of 50 joules, does 50 joules of work, okay? But then there is also something that is pulling this object up or moving this object up somehow, right, with a constant speed of 5 meters per second. And that is the applied force. Then, and they tell us, calculate the power delivered by the applied force. That indicates to us, okay, there is definitely an applied force. Okay, so just a few things to note. Remember, constant speed, right? There was 4 things for constant speed that we should note. Remember, acceleration is 0, F net is 0. But more importantly, for this section, W net is 0, okay? And delta EK would also be 0, okay? More importantly for this section. So there is a way, definitely, right, to solve this question using W net, and we'll do it afterwards, okay, for those of you who want. Again, I'm just, the instructions that I gave you, okay, to always try WNC first, I'm doing that and showing you that it's going to work and how often it will work, all right? That's in case you're stuck with the formula. But yeah, I'm not restricting you to only use this formula. If you are comfortable with WNet and you prefer WNet for some reason, and of course the question you can use it, then you may use WNet, right? I'll solve this using both. So WNC, right? There are 2 non-conservative forces. The first of which is frictional force. The second of which is applied force, okay? So work done by applied plus work done by the frictional force is equal to mg H final minus H initial plus half M V final squared minus V initial squared, right? This is delta U and delta K, change in potential energy plus change in kinetic energy, okay? So let's see, what information do we have about the applied force? Okay, we don't have any information about the applied force. In fact, in this entire formula, you'll see that the unknown that we will have is applied force. Okay, why? Because we need to calculate the power delivered by the applied force. And if you look at the power formulas, right, you will see that we actually need the applied to calculate the power, because we're going to use this one. Okay, because we have velocity, right? We don't have time. Time is not given here, so we're going to use the second power formula. Okay, so in order to use that formula, we need F applied. We need the applied force, right? This F is a force, so therefore that's going to be what we're going to calculate inside of this formula. Okay, so just keep that in mind, right? And also, just by the way, like for example, if you're approaching a question like this, understanding, so you know that the final question they ask, okay, find the power delivered by the applied force. So it's good practice to go ahead and write down your different power formulas that you could use, and look at the formulas and see what would it take for you to calculate the power. And in this case, that's exactly what we did. So we said it would take the work divided by the time. Since we don't have time, that's not going to be possible to calculate. We look at the second one. It would take the force multiplied by the velocity. Now, velocity we have, remember, it was 5 meters per second constant velocity. And the applied force, we can calculate that because, remember, we can open up this guy as what? F applied, okay, times delta x times cosine theta. Okay, so there is our applied, okay, as a variable in our equation. Okay, so just keep that in mind. It's always helpful to look at what are they asking, and then try and track backwards to see how do I actually calculate what are they asking? What is the formula to calculate what they're asking? And then in that formula, you're bound to have some unknowns, which now you need to use the diagram and the information given to calculate for those unknowns. Okay, as we're doing here, for example, right? We want to calculate power. We need force to calculate power, and to calculate the force, we need this WNC formula. Okay, plus Now, should I open up work done by frictional force? The answer is no. Okay, I should not. The reason for that is it's given to me already. Frictional force does 50 joules of work. So the work done by the frictional force is already given. Okay, if they gave the force of friction, then you'd have to obviously open it up and substitute it in, but they've given it as 50. Okay, but this is really important. It's the first time we're going through this. You have to substitute it as minus 50. This is the one tricky part about substitution or utilizing these formulas in this section, right? Normally, we don't substitute a negative force into this specific formula. However, if you remember correctly, I told you that this cosine theta will make it negative or positive, right? We can either have 0, and cos 0 is just 1, or we can either have cosine 180, which is negative 1. Okay, so we know that if a force is applied on an object in the opposite direction to the direction of motion, for example, in this instance, the direction of motion is up the slope. If there's some force that's pulling it down the slope, we would say that that's opposite to the direction of motion, right? The object is moving up the slope. This force is pulling it down the slope. Okay, so in that case, we would use cosine 180, and it would actually be a negative work done on that object. Okay, so that's what we need to keep in mind. And frictional force is definitely a force that acts opposite to direction of motion. That's almost in the definition of frictional force, right? It's a force that opposes the motion of an object. Okay, so that will always be 180, by the way. So you just need to keep that in mind when you're substituting work directly. You need to consider, is it work done in the direction of motion or opposite to the direction of motion? And then if you are given the work done, or even if you're just substituting the work done in this way, then you need to keep in mind to substitute it as a negative. Okay, I hope that makes sense. Okay, now let's fill in this MGH. So this is 3, 9,8. Height final minus height initial. So height final we actually don't have. Height initial is 0. But let's have a look at this question, right? Height final is not explicitly given, but if you remember correctly, again, I said always you can use trigonometry to manipulate the angle, the displacement, and the height on an inclined plane to either calculate one of the three, right? Depending what's given. Now, in this case specifically, I have the angle and I have what is known as the hypotenuse. Okay, and I want opposite, right? I told you it doesn't change. Maybe sometimes they might give you this, okay, but it doesn't change. Then you're still using trig, but mostly you're going to be getting this, that, and you need that or some version of that, right? So sine 30 is equal to opposite of a hypotenuse. So we call this the height divided by delta x, which is 10, the hypotenuse. So 10 times sine 30, that gives us a height of 5. Okay, so the height of this inclined plane is 5. Okay, so just always keep that in mind, right? If you don't have a height, right? Especially if you doing your question, writing out your formula, and then you realize, oh, wait, I don't have a height, then always be reminded, did I try using sine to calculate that height? Okay, so here we have 5, final height minus initial height, plus half, m is 3, v final squared. This is where it gets interesting. Okay, moving up with a constant velocity, constant speed. Constant speed / constant velocity means that the speed is not changing. So in this case, whatever speed it's traveling here is the same speed that it's traveling there. So it becomes 5 minus 5. So this whole thing actually becomes 0 because 5 minus 5 is 0. When you multiply everything by 0, you get 500. No, you get 0. Okay, let's multiply this out. This gives me 147. Let's double check that. Yeah, that's correct. Let's open this guy out here. Okay. If applied, which we want to calculate, delta x is 10 cosine. This is applied force, so this would be cosine 0. This negative 50, I'm going to take it over to that side to become positive 50. Okay. Here I'm going to get 147 plus 50, okay, which gives me 197. Here I'm going to get f applied times 10, because cosine 0 is 1. I divide both sides by 10 to get rid of the 10 on that side, and I divide this by 10, I get 19,7. The f applied has a force of 19,7 newtons. Okay. So that's how we calculate the force done by applied. Now, again, you need to be constantly asking yourself, like, okay, why did I calculate this again? Oh, yes, I calculated it so that I can sub it into the power formula to get the power delivered by the applied force. Okay, so now that we have the F applied, we can say power is equal to F times V. This is equal to 19,7 times 5. So the power delivered, remember power is in joules, 98,5, sorry, power is in watts, work is in joules. So the power delivered by the applied force is 98,5 watts. Okay, why did you not use cosine 180? Okay, that's a good question, thank you. Why did I not use cosine 180 here? Okay, so remember there's two instances when I use cosine, there's two different possibilities for cosine. I either use 0 or I use 180. I will use 0 when the force, okay, is in the direction of motion, and I will use 180 when the force is opposite to the direction of motion. Okay, I will use 0 when the force is in the direction of motion, and 180 when the force is opposite to the direction of motion. Here, this is an applied force. Okay, remember, this applied force is the reason that this object is moving up the slope. So the applied force is up the slope as well. The applied force is, in this case, is in the direction of motion. So therefore, since it's in the direction of motion, we use cosine 0. Okay, if this was, for example, frictional force, then we'd use cosine 180, but it's applied, which is in the direction of motion for this specific case, so we use cosine 0. Okay, thank you for the question. Guys, if anyone else has any questions, please feel free to ask, and I will correct it, I will rectify it, I will answer your question. Right, please. Okay, I hope you guys understood. I hope it made sense. Again, if you have any questions, please ask. Okay, let's have a look at this question. Okay, a roller coaster car of mass 200 kg with the engine switched off travels along track AB, which has a rough surface as shown in the diagram below. At point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. At point B, okay, which is at a height h above the ground, the speed of the car is 2 meters per second. During the motion from point A to point B, 3.4 times 10 to the 3 joules of energy is used to overcome friction. Ignore rotational effects due to the wheels of the car. Okay, so let's just try and put all the information that's not in the diagram in the diagram. So a roller coaster with mass 200 kgs. Okay, so we know that this roller coaster is 200 kgs with the engine switched off. Okay, so there's no applied force from the engine. Travels along track AB, which has a rough surface, ABC. Okay, so this is an entire thing that has a rough surface, so we need to consider friction. All right. as shown in the diagram below, at point A, which is 10 meters above the ground, okay, that's there. The car has a speed of 4 meters per second, that's also there. At point B, which is 8 meters above the ground, this car has a speed of 2 meters per second, that's also given there. During the motion from A to B, 3.4 times 10 to the 3 joules of energy is used to overcome friction. Okay, that's an important statement. We'll get back to that, right? So for now, everything is there. Define non-conservative force. Remember, we define non-conservative force as a force on an object, or, okay, let me think, I forget again. A force where the work done on an object is dependent on the path taken by that object. Okay. 5.2, calculate the change in kinetic energy of the car after it has traveled from point A to point B. Okay. So in this case, right, from point A to point B, change in kinetic energy, this is slightly different. Remember, change in kinetic energy is delta EK. Delta EK is equal to half mv final squared minus v initial squared. Okay, which is equal to a half times 200. Okay, v final 2 meters per second squared. V initial 4 meters per second squared. When we do this calculation, we get an answer of negative 1,200 joules. Okay. 5.3, use energy principles to calculate height h. Okay, so use energy principles to calculate height h. Okay, so okay, yeah. So energy principles, remember the energy principles that we learned are conservation of mechanical energy and WNC, work done by non-conservative force. So we're going to use WNC because there is friction, okay? But just remember, again, you're not limited to using this. Okay, the previous question I forgot to solve using WNet. I'll go back and I'll do that. Okay, so, okay, so in this case, right, calculate the change in kinetic energy of the car after it has traveled from point A to point B. Okay, this is what we calculated. We calculated this as negative 1,200 joules. Okay, moving from point A to point B. Okay, now they want us to use energy principles to calculate height h. This is at point B. Okay, so let's write out our WNC formula. Okay, let's consider what are the non-conservative forces acting on this object from A to B. So we definitely have friction, right? Because it's a rough surface, but we don't have an applied because they say that the engine was switched off. Okay, so this thing is just moving with gravity, right? It's not moving because of the engine. Okay, so WNC, this is equal to work done by frictional force is equal to half m. No, not half. This one is mg h final minus h initial plus half m v final squared minus v initial squared. So work done by frictional force. Okay, this is really important. We have to use this piece of information highlighted in blue. 3.4 times 10 to the 3 joules of energy is used to overcome friction. So this is actually the energy of friction. This is the work done by friction. If they say that 3.4 joules of energy is used to overcome the friction, you must remember the reason they're phrasing it like this is because the object is, of course, moving opposite to the direction of friction. In this case, let's just say the object is moving right, okay? Friction is trying to pull it to the left, but it's not successful, of course, because we can see that the object actually moves to the right. So because friction, because what was I going to say? Okay, I was going to say, I think, because it's moving to the right, okay, it doesn't mean that there's still no friction, right? It just means that it's overcoming the friction. Maybe the friction is pulling it. Let's just give a random example. Friction is pulling it back with 1 joule, or let's just say 1 Newton, but the applied force is 10 Newton. So of course the applied force is going to overcome that friction and still be able to push the object. Okay, so that's what's happening in this case. The object is moving to the right with the speed of gravity. Okay, yes, there is a friction trying to pull it back, but since you can see in the diagram, the object is actually moving, right? You need to understand that the object is able to overcome that friction. Okay, it's stronger. The force of gravity in this case is much stronger than that friction. So that's why they say 3,4 times 10 to the 3 joules of energy is used to overcome that friction. That means that that's how much joules of energy the friction was applying to this object. Okay, because of course this is the amount that was needed to overcome it. So that is the amount that it was applying to the object. So in this case, that 3,4 times 10 to the negative 3 is what we substitute here. Okay. However, negative, because remember, it's a work done by friction. Okay. It would have had cosine 180, which would have made it negative. This is 200. This is 9,8. Remember, we are working from A to B, right? We're working from A to B because that's the information that we have. So the initial height is 10. The final height is what we want to calculate. Final height, H final minus 10 plus half into 200 V final squared minus V initial squared. V final is 2, V initial is 4. Okay. Now you might have noticed, maybe not, we already calculated the value of this here. Okay, they wanted us to calculate the change in kinetic energy as it travels from point A to B. So keep in mind, this is it here. Remember, this formula, we are working from A to B. Okay, so this is a change in kinetic from A to B. So we actually didn't even need to open this up. We have the value. It's negative 1,200. Okay. So let's simplify things. Yeah, I simplified. I get 1960 H final minus 19600 minus 1,200. Okay. Then eventually when I do the calculation, let me just do it. Negative 3.4 times 10 to the negative 3 plus 19600. I get 20,799,996. Obviously on a round off only at the end, right? And I get an answer of, I'm getting a different answer. Why? Negative 3.4 times 10 to the negative 3 plus 1600 plus 1200 divided by 1960. 9,8 times 200. Okay, never mind. I'm just going to trust my old answer for now. If you do this calculation and this is incorrect, please let me know. Okay, but the calculations, I mean, the steps should be correct. I'm not sure exactly what's the final answer, but should be correct. Okay, but if you do it and you're getting a different answer, please let me know. Okay, so we've calculated this height now as 8,88 meters. Okay, that's how we do it. Okay, we're working from A to B. Information that we have from A to B is the power 3 or negative 3. That's a good question. It's 3. Maybe I was using negative 3. Yeah, correct. Thank you for that. 17400 divided by 1960, and yeah, you get 8.88. Okay, so that's correct. Thank you. Okay, let's have a look at this. On reaching point B, the car's engine is switched on in order to move up the incline to point C, which is 22 meters above the ground. While moving from point B to point C, the car travels for 15 seconds at a constant speed of 2 meters per second, while an average frictional force of 50 newtons acts on it. Calculate the power delivered by the engine to move the car from point B to point C. Now, in this case, okay, we have the time. Okay, remember the two formulas for power. P is equal to W over T. Okay, or P is equal to force times V. Okay, generally this is a constant velocity. Okay, so in this specific case, right, I'm pretty sure, let's just see. We could use both, right? We could use either formula because we have both constant velocity and we have the time. Okay, so we have both time and velocity. So we could actually use either one to calculate it. And they're not so different, right? Because if you have the force, you can get the work. If you have the work, you can get the force easily, right? So it really doesn't matter. 5,4. Okay. Again, we're working with a surface that has friction. So guess which formula we're going to use? WNC. Okay. Now let's consider what are the non-conservative forces acting on the object as it's moving from point B to C. Okay, so remember B, now we have this height of 8,8 and then goes up to 22 meters. What do they want? They want us to calculate the power delivered by the applied force as it's moving up. Okay, delivered by the engine. Remember, the engine is what is the applied force for this object. Okay, because the engine is moving it up the slope. So that is the applied. Okay, so here we would have applied and friction. Work done by F applied plus work done by frictional force. Okay, I'm not going to open those two up. But work done by applied, right? Do we have any information about the applied? No, we don't. Okay, but let's just say we're going to use this power formula to solve for this question. Okay, in that case, we would need the work done by applied to calculate the power done by applied. So we don't open this up. We leave it as the work. I'm going to call it the work done by the engine. Plus frictional force. Now, frictional force, remember, this is going to be frictional force times delta x times cosine theta. Okay, so we're going to calculate work done by engine, so we can substitute it into the power formula. Frictional force, it was told that while an average frictional force of 50 newtons acts on it, so 50. Okay, delta x, what is delta x? So the delta x would be the distance from point B to point C. Okay, we don't have it, which is actually a bit of an issue in this case. Okay, because you might think that, okay, wait, I could maybe create a triangle here and try and calculate delta x, because I'd be able to get this h. I can say 22 minus 88. The problem there is we don't have theta. Okay, we don't have theta, so then it's two unknowns. It's not possible now to calculate anything. Okay, this question was a bit tricky to calculate, not exactly, but kind of. Okay, they gave this piece of information. If you're going to, it says it travels for 15 seconds at a constant speed of 2 meters per second. If you're going to travel at a constant speed, you can use the formula. Distance is equal to speed times time. You're going to travel at 2 meters per second for 15 seconds. That's going to take you 30 meters. Okay, so a little bit of a different way to calculate distance, but it's just because we know that it's traveling for 15 seconds at 2 meters per second. Every second it's traveling 2 meters, so it's going to travel a total of 30 meters. okay, times cosine. Of course, frictional force will always be 180. Shift this over a little bit. Okay, delta U, this is going to be half M, which is 200. No, sorry, this is mg, 200 times 9,8. Height final was 22 minus height initial 8,8. Okay, plus half 200 m v final minus v initial. Remember, it's traveling at a constant speed, so this is actually going to be 0 because it's 2 minus 2. Okay, which is 0. Okay, then let's solve for this. Okay, let me simplify. Here I get W engine, work done by engine, minus 1,500 is equal to 200 times 9,8 times 22 minus 8.88, which is 2,571.2 plus 1,500. This is equal to 27215.20 joules. And that's the answer for the work done by the object. Power would be equal to work divided by time, which is 27215.20 divided by 15. Okay. We divide this answer by 15. We get an answer of 1814,35 watts. Okay. And that's that. Okay, I actually want to end today a little bit early. Okay, the solution to the previous one using work energy theorem. Okay, I'll send you guys that in the notes. Okay, but for now, let's end it there. Okay, and I will see you guys next week. Okay, thank you guys so much for joining. Jazakallah khair. Assalamu alaikum.